700 feet above the Golden Gate, a red-hot rivet leaves the forge like a bullet. One worker catches it in a metal can. Another drives it into the steel before the heat disappears. Around them, the tower is still unfinished. The Pacific wind is pushing at their bodies, and the water below is almost too far away to recognize. This was the next battle after the South Tower foundation. The engineers had finally created solid ground in the middle of the strait. But a foundation alone could not carry a roadway across 4,200 feet of open water. Now the project had to climb, piece by piece, cell by cell, until 2 steel towers stood higher than any bridge towers on Earth. Russell G. Cohn, the man who had guided every critical decision through the foundation crisis beneath the bay, now turned his attention upward. The Golden Gate would not be conquered by one dramatic lift. It would be raised through thousands of precise connections, moving cranes, hot rivets, narrow ladders, and men who worked where fog could erase the horizon in seconds. This is how America raised steel into the sky. The site was a mile-wide entrance between the Pacific Ocean and San Francisco Bay, with the city on one side and the marine headlands on the other. Part 1 ended at the South Pier, 1,100 feet offshore. From that small concrete platform, the bridge now had to rise vertically before it could ever reach horizontally. A suspension bridge begins with a simple force path. The roadway hangs from vertical suspenders. The suspenders pull on the main cables. The cables pass over the towers and continue into enormous anchorages on shore. The cables work in tension. The towers work mainly in compression, carrying the cable forces downward into the foundations. That logic demanded height. The Golden Gate's main span would stretch 4,200 feet between towers, while each tower would rise 746 feet above the water and 500 feet above the future roadway. Together, the 2 towers contained about 44,000 tons of structural steel. When completed, they were the tallest bridge towers in the world. But the towers did not begin in California. Their steel began in Bethlehem Steel Plants in Pennsylvania, where plates, angles, stiffeners, and connection pieces were fabricated to dimensions that had to match again after a journey of thousands of miles. In an era before digital surveying or computer-controlled cutting, accuracy was built into templates, gauges, shop drawings, and repeated inspection. The tower legs were not solid columns. They were enormous cellular structures assembled from prefabricated steel components. Inside each leg, plates and angles formed a grid of box-like cells, creating strength without filling the entire volume with metal. The components were trial-fitted, match-marked, and organized so erection crews in California could rebuild the same geometry in the correct sequence. Flat cars carried the fabricated steel to Philadelphia. From there, cargo vessels moved the tower sections down the Atlantic coast, through the Panama Canal, and north to San Francisco Bay. The pieces were stored at Alameda until the piers were ready. The supply chain linked eastern steel mills to a construction site exposed directly to Pacific weather. On the Marin side, the land-based pier was completed first. Steel plates laid on November 7, 1933, marked the beginning of tower erection. Barges delivered prefabricated sections to the site. Derricks lifted the first heavy pieces onto the base, where surveyors and iron workers aligned them over the foundation bolts and checked the geometry of both tower legs. The first sections revealed how exact the fabrication had been. Large steel assemblies could be brought together and temporarily held by drift pins and erection bolts before permanent riveting. Workers later remembered that parts fitted with extraordinary precision. The central invention was a climbing erection system. Between the two growing tower legs, crews built a traveling platform carrying derricks and cranes. From that level, the machines lifted the next prefabricated sections from barges below, swung them into position, and held them while ironworkers pinned the joints. Then the entire working platform climbed higher, and the cycle began again. This method turned the unfinished tower into its own construction support. Instead of placing one crane on the ground and asking it to reach 746 feet, the lifting machinery moved upward with the structure. Each completed tier created the support for the next. The tower rose in controlled stages, while temporary bracing kept the two legs stable until permanent cross struts connected them. Then came the Rivet Gangs. A typical crew worked as a coordinated four-man system. The heater kept rivets at the correct temperature in a small forge. A thrower sent the glowing rivet toward the joint. A catcher guided it into the aligned holes. On the opposite side, a bucker held the rivet while a pneumatic hammer formed the second head. The timing had to be exact. Too cold, and the rivet would not fill the hole correctly. Too hot, and the metal could be damaged. As the rivet cooled, it contracted and clamped the connected plates tightly together. Inspectors struck finished rivets and listened for the wrong sound. Defective work was cut out and replaced. Riveting also created another danger. The tower steel carried a lead-based primer, and red-hot rivets could release contaminated fumes when they struck the painted surfaces. Riveters wore respirators, while workers across the project used modified helmets, wine goggles, headlamps, and safety belts. These precautions were unusually strict for major bridge construction in the early 1930s. The Marin Tower was topped off on June 28, 1934, then required additional work before it was ready for cable operations. Its completion proved that the cellular design, climbing derricks, and riveting sequence could work at full scale. But the more difficult tower still waited across the strait on the foundation that had taken nearly 2 years to secure. Inside the south fender, workers completed the pier early in January 1935, and steel erection began immediately over open water. Unlike Marin, this tower had no headland behind it. Every load arrived by barge. Every mistake had nowhere to hide, but height changed everything. The Golden Gate's weather made high steel work unpredictable in ways that ground-level construction cannot prepare a man for. Fog arrived, wet enough to turn iron slick without warning. Wind gusts came from changing directions, pushing at a body while it was halfway between a handhold and a beam. Workers spent up to 20 minutes climbing just to reach their stations, then worked open-handed at 400, 500, 600 feet, where a dropped tool became a weapon aimed at the crew below. Men died. 11 workers lost their lives across the full construction of the Golden Gate Bridge. Falls, equipment failures, sudden gusts at height. The distance between a mistake and death was measured not in time, but in hundreds of feet of open air. Every shift brought men to the edge of what the human body could endure, and some did not come back from it. Joseph Strauss ordered something no major American bridge project had done before. A safety net, woven from hemp rope, suspended beneath the entire work area, would catch what the steel and the luck of iron workers could not. It cost $130,000. Contractors argued it would slow production. Engineers debated the expense. Strauss ordered it anyway. The net saved 19 lives. 19 men fell from the iron above and landed in the net rather than the bay. Shattered nerves, broken bones, close calls measured in feet, not in seconds. But 19 men who should have died did not. Those 19 formed their own fraternity. They called themselves the Halfway to Hell Club. The name was not a joke. It was a reckoning, spoken quietly by men who had crossed the threshold between the living and the dead, and found something waiting to catch them. The net became part of the bridge's story, the most human part, proof that the engineers who built the Golden Gate understood that steel and wire were not the only things worth protecting. Work continued upward. The South Tower grew through the fog, through the wind, through shifts that no man who stood at that height ever forgot. On June 24th, 1935, the San Francisco Tower was completed after roughly 6 months of erection. 2 steel towers now stood 746 feet above the water, facing each other across a 4,200-foot gap. The foundations had defeated the strait below. The towers had claimed the air above. From the waterline, they looked like nothing that had existed in bridge building before. Vertical fluting emphasized height. Horizontal struts connected the legs across the wind. Those portals were not decorative openings added after the engineering. They were part of the tower's structural system, shaped and refined into the Art Deco form seen today. The visual identity of the Golden Gate emerged directly from the logic of steel, force, and fabrication. Near the summit, workers had placed enormous steel saddles at precisely controlled elevations, ready to carry the main cables over each tower. When the cables arrived, thousands of tons of force would pass through those saddles and down the tower legs into the foundation piers below. The machines were in position. The towers were ready. On August 2nd, 1935, shipping was briefly halted while workers raised the first tramway cable between the towers. By late September, the catwalks were complete, narrow airborne platforms sagging across the strait in the same curve the main cables would follow. For the first time, a path connected San Francisco to Marin, not a roadway, an airborne scaffold built so the real cables could be manufactured in place, one pencil-thick wire at a time. Each main cable would contain 27,572 individual galvanized steel wires. No barge could deliver a finished cable of that size and lift it over the towers. Instead, spinning wheels would carry wires back and forth from one anchorage, over both towers, to the anchorage on the opposite shore, until thousands of loose strands became the 2 lifelines of the bridge. Across both cables, the project would use roughly 80,000 miles of wire. The spinning operation alone would take 6 months and 9 days. The towers were complete, but 4,200 feet of open sky still held nothing capable of carrying a highway. Now, workers would step onto those swaying catwalks and begin to spin a bridge from wire. 27,572 wires, one at a time, until the sky above the Golden Gate finally learned to carry the weight of a road.